All right, good morning everybody. So I hope magandang gising nating lahat ngayon because this would be our last session for November. I was checking the calendar kanina. Tapos, tama ano, holiday sa Wednesday, it's November 30th. Actually, ginugoogle ko siya sa kabilang window. Hold on, let me double check. Yeah, it seems it's declared a holiday. Actually, it's a regular holiday, Bonifacio Day. So wala tayong classes sa Wednesday. So the next time we'll meet would be on December 2nd na. So last November meeting na natin to. And parang it's really quite a breeze because parang kailan lang Halloween party and then kahapon ay Thanksgiving. Tapos ngayon Thanksgiving sa US and then December na. Super bilis ng mga panahon. And I am again reviewing the modules or our modules. Parang meron pang natitirang isa, dalawa, tatlong modules for Math 175. So I think we are in a good shape. I just might eat up some of your laboratory classes for some discussions. I don't know if that's a good news for you or a bad news, but I hope it's something of a relief because halimbawa sa Monday, I decided not to give you a lab excerpt just to give you some time to breathe. Ano? Kasi parang lagi na lang tayo week in and week out, you're doing something. And some of you ay medyo na-stress itong mga huling panahon kasi sabay-sabay, may 174, may 151, and so on. So yeah, it's a free day muna on Monday. Though medyo nagsisisi ako kasi nagbibilang ako. Baka kasi one meeting nga lang pala next week. So I might not be able to tackle everything or the entire module number 9 next week. So baka kakainin ko na naman yung isang Monday for laboratory exercises. So let me think about a way how to go around it. Are you guys amenable if I give you say the laboratory exercise parang take home siya? Pagsasamahin ko yung lab excerpt for chapter for module 8 and 9 into one laboratory exercise, and probably I can give it to you in a span of 2 weeks. Okay lang ba yon? Para baka lang naman, just in case kailanganin ko na magpa-discuss sa laboratory on sa Monday after next. Kasi Monday discussion na kayo. Tapos dahil isang meeting lang tayo next week, baka kailanganin ko magpa-discuss uli Monday week after next. So probably it would be a take-home exercise for you for modules 8 and 9. I don't know if that's advantageous to you, but let me think about it over the weekend, and I might be able to give kung ipapa-take home ko yung laboratory exercise completely, I'll give it to you on probably on Tuesday. All right? So malalaman nyo na by Tuesday next week kung take home yung susunod na lab exer. Magko-compensate naman ako, habaan ko yung deadline para maisingit nyo siya every now and then. But parang double-edged sword lalo na sa mga students yung yung mahabang deadline. So I hope you will not fall into the trap of relaxing a little bit and procrastinating the laboratory exercise. So kasabi nyo 2 weeks naman yung binigay ni sir, so ipapag ko na yan. Saka na lang pag malapit na yung deadline. So baka mahirapan kayo. So I suggest you do bits and pieces of it as we go along because I think madali lang naman yung topics ngayon. It's basically Newton-Cotes quadrature rules. Kahit sa Excel kaya nyo siyang gawin. So I suggest you do it as early as you can, even though I'll be giving you probably 2 weeks to finish the laboratory exercise. So yun. Kasi yung iba kasi nagpo-fall sa procrastination trap. So all right. So that's the plan. So today we'll keep it short kasi kakainin ko yung some of the time today to give you an idea of how the project will look like. So just a quick recap of what we did last time. So we're looking at quadrature rules for numerical integration. Okay. So essentially we're approximating the value of the definite integral of a continuous function f over the interval a, b. All right. Our only assumption here is that f is continuous. Because if f is continuous, or at least piecewise continuous, then we know that the integral will exist. So si f, di pala natin siya kailangang continuous sa buong interval, pero pwede siyang piecewise continuous. It could be comprised of pieces that are continuous on subintervals. But essentially, this is what you know from calculus, right? So hindi pala sorry, start ulit ako ng share screen for the benefit of those na hindi nakakakita ng screen. Yeah, and then we said there are some issues in evaluating such integrals. I think I enumerated 3, but you can think of other ones. So sa susunod na problem set, kapag ka merong essay problem na ano yung mga problema na pwedeng ma-encounter sa pagko-compute ng definite integral that will prompt the users or us to use numerical integration techniques, then you can give your inputs, ano? So wag lang kayo magpapatali dun sa tatlong binigay ko sa modules. Those are the 3 that come out of my head. Hindi ko sila kinuha sa isang reference. Sila lang yung na-anticipate ko na problems, right? So pero hindi ko alam or hindi siya exhaustive list. So baka may maisip kayo, may mabasa kayo somewhere, so feel free to share it with me, ano, para maidagdag ko siya sa module. So, but essentially, there are some issues, needless to say, for evaluating these integrals, and we want to simplify the process or to circumvent those issues. And what we did is to approximate this integral by a quadrature rule. When we say a quadrature rule, we are taking linear combinations of function values. So we are choosing say n+1 function values, and then we multiply them by some weights, some constants w sub I, and then we take the sum, and that will be our estimate for the integral. In particular, so there are several types of quadrature rules, but in particular, we looked at Newton-Cotes quadrature rules in this module. So ano yung ibig sabihin ng Newton-Cotes quadrature rules? So these are the quadrature formulas that were obtained by integrating an interpolating polynomial or the algebraic interpolating polynomial for the function f relative to some given points, right? So basically, ang ginawa lang natin dito, this is a of b, f of x dx. We said that the quadrature rule corresponding to abscissas x sub 0 until x sub n. Sorry, hanggang n lang pala yung summation. 0 nga pala ako nag-start. So a little bit of index adjustment here. So the Newton-Cotes quadrature relative to abscissas x sub 0 until x sub n for the integral of f of x dx is basically the sum of f of x sub I, yung mga given na data points sa'yo, times the integral from a to b of the Lagrange basis polynomial, okay, over the interval AB. So this is I going from 0 to n. Okay? So basically, ang idea lang sa Newton-Cotes quadrature, kapag ka meron akong ine-evaluate na integral, pwede kong palitan yung integrand by the interpolating polynomial. And then integrate the interpolating polynomial instead. And if you carry it out theoretically, you will get this formula. Right? So it is easy to notice that indeed this is a quadrature rule, because it compares nicely to the general form. You have your f of x sub I here, and then the weights are basically the integral of the Lagrange interpolating polynomial. Okay. By the way, parang hindi ko nakikita sa screen ko yung annotations ko. Can you see my yung laser ko in the screen or no? Parang nag-stuck yung share screen ko sa laptop ko. Hello guys, am I still here? So hindi nga nakikita, no? Probably internet connection problem. Let me restart my screen sharing. Okay. Oh, by the way, guys, while dealing with this technical issue, hindi ko pa rin tapos checkan yung problem set, pero I'm done grading all PS 1.1 and PS 1.2 submitted via Canvas. So today I'll start grading PS 1.3. I know I promised natatapusin siya ngayon, but sinabi ko naman pwedeng humingi ng konting extension over the weekend, but I'll try to grade it. Once I graded everything in Canvas, I will now comb through my email and look at those ng mga nag-request ng late submissions. All right, so chill lang kayo muna. Yung mga nag-email sa akin, you'll probably get a reply over the weekend. Ano? So yeah. Okay, so I hope things are fixed now. Oh, there we go. I can see my laser now. So yeah, those are Newton-Cotes quadrature rules. And in Newton-Cotes quadrature rules, there's no requirement on the choice of the exabytes. The exabytes can be freely chosen all over the entire integration interval. All right? So hindi kailangan equally spaced, hindi kailangan hindi kailangang prescribe yung mga exabytes. You can choose it whatever you want. If you want to get the Newton-Cotes quadrature rules that minimizes the L infinity error, so you can choose the exabytes to be the roots of the Chebyshev polynomial. If you want to minimize the L2 norm of the error in the integration, then you could choose the exabytes to be the nodes or the roots of the Legendre polynomial. So you see, ang dami nating pwedeng pagtahi-tahiin na konsepto, no? So even if I won't explain the details of using Chebyshev and Lagrange basis polynomials, baka halimbawa sa problem set, meron dong isang integrative question. And I tell you, kaya lang na-defeat na yung purpose, in-spill ko na siya ngayon. Pero one possible question that I am thinking is, probably if I will test if you can assimilate or accumulate this little learnings that you got from previous chapters na sabihin ko, i-derive nyo yung gamitin nyo yung Newton-Cotes quadrature formula that will minimize the L2 error of the in the integration process. So even though I didn't give you the entire process, dapat alam nyo na, gusto ni sir ma-minimize yung L2 norm ng error. Yung Newton-Cotes, nakadepende lang naman siya sa interpolating polynomial. So in turn, the problem is now reduced to ano yung interpolating polynomial na may minimum L2 error. And then you'll review your notes from chapter 1, you will realize, Legendre nodes yung gagamitin ko. So those properties that we have discussed under chapter 1, lahat ng properties ng AIP are inherited by the Newton-Cotes quadrature formulas. So I hope you can make that connection. Kasi baka ganun yung ibibigay ko sa problem set, or at least one of the questions there. Okay? Now, but in this problem, all right, so dahil ina-assume ko na kaya nyo ng pagtahiin lahat ng halos yung mga konsepto na napag-aralan natin sa chapter 1 at saka dito sa Newton-Cotes quadratures, so I just focused the discussion here when we are choosing the exabytes to be equally spaced points. But again, there's nothing restricting you from choosing the exabytes or to choosing exabytes to be equally spaced nodes. Hindi kailangan sila ay equally spaced points. But for convenience and for elegance of derivation, inassume ko lang dito na yung ating mga exabytes ay equally spaced. And with that assumption, I can define two further classification of Newton-Cotes quadrature rules. But again, these two classifications are not exhaustive, all right? Merong mga quadrature rules na hindi papasok dito sa, actually, hold on. Exhaustive pala sila. Lahat ng mga Newton-Cotes quadrature ay magpo-fall into two categories. Una, pwede siyang closed formula at pwede siyang open formula. When you say closed formula, x of 0 is equal to A and x sub n is equal to B. Required. Nakasama yung endpoints doon sa ating interpolatory abscissas. And open formula kapag hindi siya closed. So ito yung mga not closed na formula. Okay? So ibig sabihin, hindi kasali, or actually, yeah, hindi kasali si A or B doon sa inyong derivation. Okay? And the most popular among the closed and the open formulas are those where the step sizes are fixed. So sa closed formula, meron kang interval A to B, nag-start ka so dapat si A kasama sa abscissa, so that's x sub 0, tapos si B ay x sub n dapat, and then you get x sub 1 here, x sub 2, x sub 3 until x sub n, and we are assuming there's a uniform step size h between the nodes. Okay? That's why in that case, baba ko lang to ng konti, in the case of closed formulas, we're getting n plus 1 points. The two endpoints are included. So here, the value of h is b minus a all over n. And x sub I is equal to a plus what? Plus I delta x plus IH, where I is from 0 until n. Okay, so yan yung formula na kailangan nating tandaan for closed formulas that have that uses equally spaced points. Now, in contrast to open formulas, the open formulas hindi kasali yung a and b dun sa interpolatory abscissas. So x sub 0 is somewhere here, x sub 1 is here, x sub 2 is here, until you reach x sub n right before you come to b. So hindi sila kasali. And now, so ibig sabihin, we need to divide the integration interval into how many subintervals? Into a number of subintervals, or the number of subintervals in a closed formula plus 2. All right? So kasi bakit magkakaroon ka ng additional 2 subdivision points? Kasi nga hindi kasali si A at saka si B. Right? So if you will count this, you will have n plus 3 data points under consideration, but you're gonna use just n plus 1 of them because A and B should not be part of the interpolation process. So here, h is b minus a all over n plus 2. All right? N plus 2 siya kasi kailangan mo ng n plus 3 subdivision points. Magsaserve si A at saka si B na subdivision points, pero hindi sila kasama dun sa interpolation. So even though we come up with n plus 3 subdivision points here by using the step size b minus a over n plus 2, hindi naman kasali si A at saka si B, so we'll still get a degree n interpolating polynomial. Tapos yun yung i-integrate natin for the closed formulas. Okay? And now here, the formula for x sub I is a plus I plus 1 h, I going from 0 until n. Okay, so medyo magkaiba yung pagko-compute ng step size nila. Kasi sa open formula, kailangan mo ng additional 2 points. Or, yeah, additional 2 subdivision points kasi dun sa interpolation, hindi mo isasali yung dalawang endpoints. So basically, kailangan ko i-amend yung sinabi ko kanina, sorry. Pag open formula, ibig sabihin hindi siya closed. So ibig sabihin, hold on. Kailangan ko talagang i-amend yun. Wala akong lusot. Kailangan kong baguhin yung sinabi ko. Kapag ka siya ay open formula, ibig sabihin, restrict natin to sa A and B are not interpolatory abscissas. So kailangan kong susugan yung sinabi ko kanina na exhaustive, yung classification ng Newton-Cotes quadrature into closed and open formulas. So kasi sa closed formulas, dapat kasali parehas si A at saka si B. Sa open formulas pala, dinefine ko to sa module na si A and B ay parehas hindi interpolatory abscissas. So there are still some quadrature formulas or Newton-Cotes quadrature formulas that will fall between closed and open. So meron kang half open and half closed formulas wherein only one of the two endpoints are part of the interpolation process. And that's another possible class of Newton-Cotes quadrature rules. But we usually use this two, closed at saka open formulas. Closed formulas are preferred whenever you don't have any problem with the with the integrand. But if the integrand has a discontinuity at the endpoints, especially if it's an essential discontinuity, wherein the function values does not exist at A and B, so magkakaroon ka ng improper integral, so ayaw mong isama si A at saka si B doon sa interpolation process kasi nga posibleng walang function value si F doon sa A at saka si B. That's the case for improper integrals, right? So kapag ka improper yung integral, but you know that the integral exists, yun nga lang, kailangan mong i-turn into a limit kasi walang function value sa A at saka sa B, then open formula yung preferred na gagamitin, which gives me an idea sa susunod na problem set. I might ask you na kailan preferred yung open formulas over closed formulas. So kindly take note of that and remember na siya ay ginagamit siya yung choice kapag ka may improper integral, especially if there are essential discontinuities at the endpoints of the integration interval. Okay? And I think sinimulan na natin to last time, the derivation, when I showed you in details how the trapezoidal rule, which probably you knew since senior high, tama ba? Senior high, nag-trapezoidal rule na kayo? Kung matandaan kung nasa DepEd, kung nasa DepEd competencies for grade 11, I wrote a book ng ng calculus for senior high. Hindi ko maalala kung nagsulat ako about trapezoidal rule and probably the midpoint rule because those two are the most basic integration formulas. But yeah, I hope this is not the first time that you're seeing it, pero wala rin naman disadvantage kung ngayon lang ito nakita. But essentially, the trapezoidal rule is the quadrature rule I sub 1 that is a closed formula. Ang notation natin, yung I sub n, siya ay isang Newton-Cotes quadrature rule obtained by integrating an algebraic interpolating polynomial of degree n. So gumamit ka ng n plus 1 points para ma-interpolate si f. Kasi nga nagbago ako ngayon ng subscript. Nagsimula ako sa 0, natapos ako sa n. So essentially, I still have n plus 1 points. I have n plus 1 points, so my interpolating polynomial will be of degree at most n. Tapos pag in-integrate ko yung p sub n na yon, I will get I sub n, which is my approximate for the integral of little f over the interval ab. And if I derive the closed formula consisting of 2 points, so meron ako interval AB, gusto kong gamitin yung 2 points, tapos sinabi ko closed dapat yung formula, so si A and B na yung choice ko. And by definition, this would be the smallest possible closed formula because walang closed formula na isang point lang yung ginagamit. Kasi sa closed formula required, nakasali si A and B. So we will have at least two abscisses in the closed formulas, the closed Newton-Cotes formulas, and we will get the interpolating polynomial that will pass through a comma f of a and b comma f of a, but basically that will just be a straight line passing through the 2 points. And essentially, kung i-integrate natin etong linear function to, that will just be the area under the graph of this linear function. So basically, it's just like taking the area of a trapezoid. And basically, that's how the area of the trapezoid is computed. And that's why, essentially, itong formula na to, tinatawag natin na trapezoidal rule. And actually, it's quite easy to implement even kung ayaw nyo na mag-MATLAB, gusto nyo Excel lang yung gamitin, it's fine. Kasi napakadali namang i-Excel ng trapezoidal rule. Because you just need 2 function values and then multiply each by their common weight. Parehas yung weight ni f of a at saka ni f of b parehong b minus a all over 2. Right? So, kunin mo lang yung sum ng function values, then divided by, multiply it by b minus over 2, then you get an approximate for the integral. Okay? How good is this approximation? We'll say later. But essentially, this is as good as the interpolatory process. Okay? Now, you can play with the other formulas here. I enumerated some of the other closed Newton-Cotes quadrature rule. Have you guys heard of the Simpson's rule? Tanda ko ng Math 36 namin, merong Simpson's rule. Kasi ito yung pinakaayaw ko talagang topic. Kasi sa Math 36, parang ang dali namang mag-integrate. Tapos bakit pa merong mga formulas na to? I really hate memorizing formulas. So hate na hate ko tong mga numerical integration techniques. Pero ang laking tulong pala niya. Kasi nga, hindi lahat ng function madaling kunan ng integral or ng antiderivative. So the Simpson's rule is basically a 3-point closed Newton-Cotes quadrature formula. So essentially, we are choosing 3 equally spaced points over the interval A and B, A comma B, A and B included. So ibig sabihin, kung tatlong equally spaced points sa AB, si A at saka si B kasali, so we only have one candidate, and that would be A plus B over 2, the midpoint between them. And then we get the interpolating function that will pass through the points determined by these three abscissas. Meron kang tatlong points, so ibig sabihin meron kang at most quadratic interpolating polynomial, and then instead of integrating f, you integrate that quadratic function over the interval AB, and you're going to get a number which we will denote by I sub 2 of f. Tapos pag in-evaluate mo to theoretically, you'll be able to derive this. Okay? Makikita nyo, really, tatlong function values lang yung ginamit niya. Okay? The 3/8 rule ay 4-point closed formula. So ginamit ko si A, si B, tapos si x1 at saka si x2, where x1 and x2 are computed this way. Okay? So basically, ang ginawa ko lang, halimbawa, interval AB to, no? So ang formula sa closed Newton-Cotes quadrature ay B minus A over N. Here, our N is 3. Kasi ang gagamitin ko ay si x sub 0, which is A, tapos si x sub 3, which is B. Kailangan ko ng 4 points eh. So nag-start yung bilangan ko sa 0. So x sub 0 until x3. Then I'm gonna get x1 here and x2 here. Pero sa tatlong interval ko lang naman hinati yung AB. So kaya ang step size ay B minus A over 3. So that means x1 is A plus B minus A over 3. And then x2 is A plus 2/3 B minus A. And then the third would be, or the fourth would be B. Tapos, kunin mo yung interpolating polynomial na padadaan sa x sub 0, x sub 1, x sub 2, and x sub 3. You integrate that cubic polynomial, then you're gonna get this formula, the 3/8 rule. At ganun din yung Boole's rule. So Boole's rule, ilan ang ginamit niya? 5 points yung ginamit sa Boole's rule. So that's gonna be I4. Okay? So is the derivation clear? Hindi ko na kailangan ipakita yung pag-i-integrate ng interpolating polynomial. I hope it's fine. Okay, gawin nyo lang symbolically. So at least try one of them. Kasi baka pag may theoretical part yung problem set, ipa-derive ko yung isa sa mga ito. So be ready for doing that. Pero nag-i-integrate ka naman lang naman ng Lagrange polynomial. So I hope that is okay. And then I want to present yung open Newton-Cotes formulas. So sa open Newton-Cotes formulas, again, hindi kasali si A and B. So here, you can start with the smallest, which is a 1-point open Newton-Cotes quadrature rule. Ano ang acronym ko sa open Newton-Cotes quadrature rule? ONCQR. So ONCQR. 1.0 NCQR. So, ibig sabihin, si x sub 0, si A ay hindi kasali, si B ay hindi kasali, pero kailangan ko ng isang point. At ang idea ko rito ay sana equally spaced siya, or if you use the formula delta x, or which is our h, B minus A over N plus 2, so that will give you the midpoint. Kasi here, ang gagamitin kong ang n ko ay 0 kasi gagamit lang ako ng isang point. So I want a constant interpolating polynomial. So here I'll get, when n is 0, I'll get B minus A all over 2. So that means I will use the midpoint. Okay? Kukunin ko yung function value dun sa midpoint, tapos kukunin ko yung interpolating polynomial na dadaraan dyan sa midpoint. So yung interpolating polynomial na dadaan sa midpoint would be the constant polynomial. Okay? So if you use Lagrange form, tapos isang point lang yung ginamit nyo, makukuha nyo ay yung constant polynomial corresponding to the function value of, or the function value at A plus B over 2. Tapos kukunin mo yung area under this region, yan yung integrate mo, pero ito lang naman ay isang rectangle, right? Ang area niya ay B minus A times whatever the function value you have here. But that function value is evaluated at A plus B over 2. So ito yung width, ito yung length. So indeed, ito yung midpoint rule, right? So yan yung approximate natin para sa integral using only 1 point. So it's a 1 point ONCQR. Now, if you are patient enough and if you want to use some more points, you can try to derive higher order 1 point ONCQRs by again using the appropriate points. Okay, using the formula for H, the formulas for exabytes, and then integrating the resulting interpolating polynomial, you're gonna get this these formulas. Okay, so also try to derive these formulas to replicate the solutions. So yeah, I'll leave that to you. But I hope you get the idea, the general process behind Newton-Cotes quadrature rules. Okay. Now I have here an example which implements itong quadrature formulas. And I don't think I need to give too much details on this because it's just a straightforward application of the formulas. Unless you have some questions, probably I can address them. But what I am more interested here would be the error analysis. And as interpolation theory tells us, up to some point, up to some point, prior to Runge phenomenon kicking in, the more points we're using, the better the interpolation is. Tama? Pero wag mo masyadong damihan yung points kasi pag masyado nang mataas yung degree ng interpolating polynomial, nagiging susceptible na tayo sa Runge phenomenon, and the Runge phenomenon has a very big effect on the value of the integral, right? Kasi sabi natin yung Runge phenomenon, ito yung ito yung very fast and high scale oscillations in the interpolating polynomial. So pwedeng mag-wiggle yung polynomial. Pag malalaki yung wiggle, malaki yung area under the curve. So yung error na na-incur mo due to the Runge phenomenon will have a huge effect in the error in the Newton-Cotes formula kasi nga nag-integrate ka area under the curve. So kung masyadong malaki yung wiggle o yung oscillation dun sa interpolating polynomial, ibig sabihin malaki rin yung kino-contribute nun na error dun sa integral. Kasi kinukuha mo yung area under the curve. All right? So that's why we need to be very extra careful when using more points. Pero the idea is the more points, the better, right? Yun yung sinasabi ng interpolating polynomial, again, except kapag ka may Runge phenomenon na nakasali. So let's try to see if among the formulas that we used, mag-hold ba yung ating hypothesis that the higher the value of n, or the more points you use, the better the approximation, as long as walang Runge phenomenon. Okay, so and that's what I did here. I approximated the value of ln2. So ito yung usual way paano mag-validate ng isang formula na dinerive nyo bago nyo siya i-implement sa isang uncertain scenario. Try to use some baseline examples just to see how good your method is. Okay, at yun yung ginawa ko rito. Alam ko ang eksaktong value ni ln2. Right, ln2 is the integral from the integral of 1 over x from 1 to 2. So I can use this as a benchmark test para tingnan ano yung accuracy ng mga methods na ginagawa ko. So instead of integrating by hand itong expression na to, which will give me exactly ln2, pwede kong gamitin yung mga Newton-Cotes quadrature formulas na meron tayo. So when you use trapezoidal rule, you'll get 3/4. Kapag ka Simpson's rule, 25 over 36, and so on. So I will compare it with the actual value. And again, pag nagko-compare kayo sa actual value, you use relative errors. So sa trapezoidal rule, 3/4 yung estimate, I have 8.2% error. Pag Simpson's rule, 25 over 36, I get 1.87%. And it seems to be a huge improvement, right? Kasi sa trapezoidal, gumamit ka ng 2 points. So 2 function evaluation yung kinary out mo. So that will give you 8.2% error. Pero pag nagdagdag ka pa ng isang function value evaluation, pag nag-Simpson's rule ka na, 3 function value yung kukomputin mo, tapos basic arithmetical operations lang yung gagawin mo, you will get 25 over 36, but the error now is down 8 times. So from 8.2%, it's down to 1.87. Hindi pala almost 8, mga around around 4 times yung nabawas dun sa error. Okay? Now, if you go further, 3/8 rule, kung kaya mo naman gumamit ng 4 na points, why not use 3/8 rule, 111 over 160, and that will give you a good error, 0.09%. And then kung talagang kayang-kayang mo pandamihan yung function evaluations, pwede ka mag-Boole's rule. Pag Boole's rule, 4367 over 6300, ang relative error niya ay 0.004%. Okay? So indeed, at least dito sa hanggang sa Boole's rule ay the more points the better. Actually hindi lagi sa Boole's rule, pero para sa Boole's rule at para dun sa ating function f, mas okay yung mas maraming points. At least hanggang sa Boole's rule. Meron tayong numerical evidence. Alam ko na siguro yung nangyari bakit nagkaganito yung Boole's rule. Kasi siguro nag-control H ako dito, find and replace. Ni-replace ko yung Boole's rule, ni-replace ko yung bool ng Boole's rule. Kaya nadoble yung rule. Sorry. Okay. Now, you can also try the open formulas. For the midpoint rule, you'll get 3.82%, which is quite interesting because the midpoint rule, which used only 1 point, is much accurate than trapezoidal rule, which used 2 points. Okay. Pero that is not always the case. That just happened here for the specific function 1 over x. Pero hindi laging ganon, alright? So medyo nakadepende rin kay f yung error. Because again, pag dinerive niyo yung theoretical error dito, ang error dito ay integral ng error mula sa interpolation, which could be another possible problem in the problem set. Hindi ko diniscuss or hindi ko i-discuss in details yung error in Newton-Cotes formulas. Kasi nga siya lang naman ay error ng interpolating polynomial integrated over the given interval AB, then that's it. You get the error bound. So I don't think I need to use that. As math majors, you can connect the dots. You can accumulate this little concepts. So yon, midpoint rule, and then 2-point OCNR, 2.62%, 3-point open formula, 0.15% error, and then 4-point open formula, 0.11% error. But in all of these, we see that Boole's rule gave us the best approximation. Now, if you want to investigate more, right? So pwede nating tingnan, ano kaya to graphically? Paano work yung process? Again, you trace it back to interpolation. So dun sa mga closed formulas, so ang ginawa ko lang, meron akong exact integrand, 1 over x. That's the blue curve here. I don't know if you can still see the blue, but here's the blue curve. Somewhere there, yan yung blue curve. Nandyan yung exact function. Pero kapag yung function sa Newton-Cotes quadrature rules ay pinapalitan natin ng interpolating polynomial. So in the case of the trapezoidal rule, okay, gumamit ako ng 2 points. Pero closed formula to. So kailangan gagamitin ko yung function value kay A, function value kay B, and then kukunin ko yung interpolating function passing through those 2 points. So that's going to be a linear function. Actually, that's the yellow line you see here. Ito yung inintegrate ko instead of the integrand. So yung integrand ko nandito. So makita nyo, meron talagang discrepancy. Yun yung magre-represent ng error. So kung gaano kalayo yung interpolating polynomial mula doon sa actual integrand, okay? So kunin mo lang yung integral ng difference sa kanila. Kasi nga area lang to under the curve. So pag kinuha mo to, yan, ang makukuha mong area using the trapezoidal rule ay ito. Walayan ko siya ng... Ito yung makukuha nating area using the trapezoidal rule. Tapos, yung actual integral ay yung area under the actual function. So, hulayan ko yung integral para sa actual function. Nandito yung actual function ko. Okay. So yan yung kulay pink, siya yung tunay na integral, yan yung tunay na area under the curve. Yung kulay yellow, siya yung area, siya yung approximate natin using the Newton-Cotes quadrature formula. And you see that there's a discrepancy. This is the discrepancy. Kulayan ko ng kulay, what? Kulay blue yung discrepancy. So itong area ng blue region, ito yung nagre-represent ng discrepancy or ng error between the estimate from the Newton-Cotes quadrature formula and the actual integral. So kailangan kunin natin yung area nitong blue region. Pero ano yung area ng blue region? It's going to be the interpolating polynomial or the integral of the interpolating polynomial. Oh, sorry, line nga pala yun. Minus the integral of the function f. Kasi nga, area under the curve, up minus down, area between curves, right? So area ng interpolating polynomial, so that's going to be the integral of p sub n minus integral ng function f. Or actually, pwede mo siyang isulat in a single integral. So it's going to be the integral of p sub n minus f dx. From A to B, yan yung area ng blue region, right? But essentially, this guy is, sabi ng interpolation theory, p sub n minus f. Ito yung error galing sa interpolating polynomial. So it's gonna be f to the n plus 1, kung ilang points yung ginamit mo. Here we use 2 points. So basically, this is f triple prime. Gumamit ako ng 2 points. So ibig sabihin, this is f double prime of c over 2 factorial times omega of x dx. So ito yung error term. Yan yung area nung discrepancy, nung blue region, right? But we cannot compute for the actual area because we don't know what this constant is. All right, gumamit ako ng 2 points. So ibig sabihin n plus 1 factorial 2 points. Yeah, second derivative. Okay, so yeah. Hindi ko ito ma-evaluate exactly because we don't know what f double prime of c is. All we know is that c is a number between a and b. So ang gagawin nyo lang, pwede nyo itong hanapan ng upper bound. So the absolute error will be bounded above by the absolute value of f double prime of this integral. Okay. Tapos, pwede mo itong lagyan ng upper bound. Oh, actually, equal pa to. Tapos, pwede mong paglaruan yung mga expressions dito. You can have f double prime of c, just a constant going out. And then integral ng absolute value ng omega dx to avoid the cancellations inside. Okay, pero less than or equal na to kasi pinasok ko yung absolute value sa loob ng integral. Ang absolute value ng integral ay less than or equal sa integral ng absolute value. That's triangle inequality for integrals. So essentially, pero si omega given, si omega ay product ng x minus x sub I going from 0 to n. Okay, so this can exactly be computed. You can replace this by the upper bound and then all over 2 factorials. So pwede mo itong gawing less than or equal to sa m over 2 factorial times this guy. Oops. And that would be your error bound. Sabi ko hindi ko i-discuss in details pero diniscuss ko rin naman. So sorry about that. Pero yun yung idea. And then, I also have a figure here showing naman yung open formulas. And you see sa open formulas, hindi mo talaga dinaraanan, hindi nagpa-pass through yung interpolating polynomials sa A and B. So ito si A, oops. Ito si B. Okay. Yung midpoint, kinuha ko yung straight line. Yan yung midpoint rule. But you see that for all the other interpolating polynomials for the open Newton-Cotes quadrature rules, hindi sila nag-intersect with the actual function value. Yung sa purple mukhang muntik na, pero hindi pa rin sila nag-intersect. Right? Kasi nga yun yung idea, hindi dapat kasali si A and B dun sa interpolation process. Okay? All right, so I think that's all that I want to say about this module. The rest of the module will be discussed on Monday. So kindly or make sure you attend your lab classes kasi doon nila i-discuss yung composite trapezoidal and composite Simpson's rule. Now, quickly, para saan yung composite rules? Well, gusto natin the more points the better, right? Pero sabi natin, kapag ka dinamihan mo masyado yung points, pwede kang mag-suffer sa Runge phenomenon. So to avoid the Runge phenomenon, ang ginagawa natin, hinahati natin yung integral into several pieces. So parang ano naman to, parang splines yung datingan. So instead of applying, or if you have an interval AB, and then you have various points on it, x, x1, x2, x3, x4, and so on. Marami kang points na gagamitin. Pero dahil baka magkaroon ng Runge phenomenon, so ina-avoid mo yung paggamit ng sobrang laking interpolating polynomial, ang gagawin mo, i-approximate mo muna yung integral from a to x sub 1 using trapezoidal rule. Kunin mo yung itong area na to, tapos siguro drawing ko yung function, no, para mas maganda. Halimbawa, ito yung interpolating polynomial na nakuha ko. Meron siyang Runge phenomenon. So to avoid the Runge phenomenon, instead of integrating the actual integrating polynomial that will pass through all of the many points that we have in this process, ang gagawin ko piecewise linear interpolant para paulit-ulit lang ako nagtra-trapezoidal rule. So instead of integrating the pink curve from x1 to x2, which represents the integral of the large degree interpolating polynomial, mag-ano lang uli ako, mag-trapezoidal rule ako on the interval x1 to x2. So basically, I will replace the high degree interpolating polynomial by the piecewise linear interpolant, and that's what I will integrate on the second piece. And I'll do this for all of the pieces. So in turn, nag-trapezoidal rule lang ako sa mga subintervals, then I'll use the additive property of integrals para makalculate yung actual integral. Okay? So para ma-avoid ko yung pagkakaroon ng Runge phenomenon. Okay? But the formula, the derivations, and the error analysis will be discussed in your lab classes on Monday. Sabi ko, ang iksi lang ng klase ngayon, kaya nagmamadali ako kasi 9:18 na pala. Dapat ipapakita ko yung magpapakita ako ng sample projects, but probably I can do that on Friday, start ng Friday meeting. Kasi anyway, magpapadiscuss na ako for sure sa Monday after next sa laboratory classes, kalahati ng module number 9. So kasi ang gagawin ko muna, first 10 minutes ng next class natin ay sample projects, But I already enabled sa Canvas yung module consisting of the project guidelines, specifically the project guidelines from last year. I will be just adapting them. So yun na rin yung gagawin nating guidelines. So ang gagawin ko na lang, pakibasa yung guidelines na yun. Nasa Canvas na siya. I-download nyo tentative project guidelines, but most probably yun na yung gagamitin natin for this semester. And then at the start of the class on Wednesday, I'll show you some of the projects, some of the good projects that I have. Though makikita nyo ron na estudyante pa si Sir Jacob, estudyante pa si Sir Angelo, So mga estudyante ko kasi sila ng 174 nun. Pero hindi pa naman ako ganun katanda. Magkakasing edad lang naman kami halos. Kunwari. Anyway, so yun yung papakita ko sa inyo, yung projects nila next time. All right? So I'll stop here. Sabi ko ang iksi lang, naubos ko pa rin yung oras. But do you have some urgent questions or concerns? Wala naman. So watch out for the problem set over the weekend or your score in the problem set over the weekend. Tatry ko siyang tapusin mamayang gabi. Pero kung nagkaka-anxiety attack kayo kapag ka nagdo-notify si Canvas, lalo na pag nag-grade ako, i-mute nyo na muna yung notification ni Canvas. Kasi usually night shift ako. Parang ang ko kasi ang productive hours ko ay siguro pagkatapos ko mag-Netflix ng mga 12 midnight. Siguro mga 1 to 3 a.m. yun yung most productive hours ko. Tapos nag-adhere ako sa Pareto principle. I don't know if you have heard of the Pareto principle. It says that 80% of our most significant works happen during the 20% of our working time. So ibig sabihin, dun sa 20% na nagtatrabaho ka, 20% ng times na nagtatrabaho ka, dun mo nakukuha yung 80% ng output mo. So, dinadaya ko yung Pareto principle. Doon na lang ako nag-work sa supposedly 20% nung workday. Kasi doon ko naman magagawa lahat. Marginal lang yung nako-contribute ng remaining 80%. So, why work? I'll just Netflix and chill. So, ganun yung filosofiya ko sa buhay. But anyway, so I'm blabbering here. So, if you don't have any questions, thank you guys for joining me today. Enjoy the weekend. I will not meet on Wednesday, but see you on Friday. Bye, guys.